So, I will discuss about the experiment to measure the magnetization of a magnetic material, ferromagnetic material. So, you know that different kinds of magnetic materials, these ferromagnetic materials, antiferromagnetic materials, ferrimagnetic materials, paramagnetic materials, diamagnetic materials, right. So, whatever now I want to discuss, that is ferromagnetic type of material, and how to measure the magnetization of ferromagnetic material as a function of magnetic field. That experiment I will demonstrate. So, before that, let me discuss about the theory of this experiment or working principle of this experiment. So, here measurement of magnetization of ferromagnetic material, right. So, what is magnetization? So, ferromagnetic material, any material is made of atoms. So, atoms have in magnetic material. So, each atoms have basically magnetic moment or magnetic dipole moment. Okay. So, now this dipole moment in ferromagnetic material, dipole moment, it form the domain, basically it form the domain, means group of atoms in a certain region. Okay, they interact with each other, they have exchange interaction, and they form a region. Within that region they have exchange interaction. Okay. So, that region is called the domain. So, these ferromagnetic materials have many domains, and these domains, so each domain have total magnetization, total magnetic moment in a certain direction. So, now you can think there are many domains, and each domains have magnetic moment, dipole moment, okay, giant dipole moment, and these dipole moment are randomly oriented. So, net moment of the sample is 0. So, we express this phenomena, we express this moment of the material in terms of magnetization. Okay. So, it is basically independent of the volume of the material. So, magnetic moment per unit volume, that we tell the magnetization. Okay. So, magnetization is basically defined as magnetic moment per unit volume of the material. So, total moment of the material, it depends on the dimension of the material or volume of the material, but magnetization is independent of the volume of the material, it is per unit volume. So, now there are different parameters we use for magnetic material, okay, to define the magnetic material. So, what are those parameters? This is susceptibility, permeability, right. So, it depends on susceptibility of the materials. Magnetic material is defined as m by h. Okay. So, chi equal to m by h, that is susceptibility, and permeability is a mu equal to mu 0 mu r. So, mu 0 is the for vacuum, permeability for vacuum, and mu r is the relative permeability of the material. Okay. So, relative permeability means with respect to permeability mu by mu 0. Okay. So, that is mu r, relative permeability, and this permeability is related with the susceptibility. So, mu 0 1 plus chi. Okay. So, that means that chi is related to m by h. Okay. So, mu 0 is air permeability or permeability in vacuum, it is the constant, is the this value. So, here you can see another term we use, that is the magnetic induction B. Okay. B is related with this applied magnetic field H and the magnetization of the medium. Okay. So, this is mu 0 H plus M, that is the B. So, the B is basically mu H, B is basically mu H. Okay. So, from here you can see that if we measure magnetization as a function of magnetic field, then all information we will get. So, we can find out what is the chi susceptibility of the material, what is the permeability of the, if find out chi, then what is the permeability of the material we can calculate. Okay. And then we can find out, if we measure M as a function of H, what is the B, we can find out, or yes, we can find out. So, M magnetization as a function of magnetic field, if we can measure, then basically we will know about the magnetic property of the material. So, that is why it is very important to measure magnetization of a material, ferromagnetic, especially ferromagnetic material we will use in our laboratory. So, purpose why we should measure. So, purpose is this, to know about the magnetic property of this ferromagnetic material, and this is a very famous hysteresis loop. If it is ferromagnetic material, so we should get the hysteresis loop. So, this dotted line, it is telling basically, if you start from the zero magnetic field and then goes at maximum magnetic field, okay, start experiment from there. So, you are decreasing field, it will go and negative field, then maximum negative field, then decrease and coming back to the 0 and then to the highest magnetic field. So, then you get the hysteresis loop, MH loop or BH loop. So, one can here plot MH or B also, because if B can find out, if you know M, so H plus M, that is B. Okay. So, BH loop or MH loop, this is a very famous for magnetic material. If you measure this one, so you will know what is the coercivity of that ferromagnetic material, what is the remanent magnetization of the material, okay, what is the saturation magnetization of this material, for that what field you need. So, basically this, what is the saturation value of magnetization, this you can find out. What is the remanent at zero magnetic field, what is the magnetization, that is remanent magnetization, at which field this M becomes 0. So, that is the coercivity, or we tell switching field. So, you see that you can see this at this magnetic field at coercivity. So, if slightly field increase or decrease, then direction of magnetization from positive to negative, negative to positive, it goes. Okay. So, that means that it switch, this magnetization switch from this one direction to the another direction. So, that is why this coercive field we tell sometimes the switching field for the magnetization. Okay. So, this experiment we want to do in our laboratory, teaching laboratory. Now, how to measure the magnetization as a function of magnetic field. Okay. So, there are different experimental technique for measuring magnetization as a function of magnetic field. So, very famous techniques, and frequently used in our laboratory, especially research laboratory. So, one is vibrating sample magnetometer, VSM, okay. Vibrating sample magnetometer, then superconducting quantum interference device, QUIT magnetometer, then magneto-optical Kerr effect, MOC, then cantilever beam magnetometer, CBM. There are other techniques also, but these 4 techniques are very popular. Although last one is not very popular, it is the specialized technique I used in my research laboratory, but other 3, especially these 1 and 2, these are in research laboratory. These 2 are frequently used. This third one also in many laboratory it is used, but last one is used in few laboratory. But all this called magnetometer, because it is this technique, this magnetometer is used for measuring the magnetic property of the magnetic material. So, magnetic property, you, as I told that you want to know susceptibility, you want to know permeability, you want to know magnetic induction, you want to know Curie temperature. Okay. So, using this magnetometer one can get all this information. Okay. So, there are 4 techniques, but so one of them you can use. So, in our laboratory, teaching laboratory, we use this VSM, vibrating sample magnetometer. Okay. So, what is VSM? What are the working principle of VSM? Let me tell you. So, working principle of VSM is not very difficult. It's a simple. So, I have a magnetic material, ferromagnetic material. Okay. You can take cobalt, nickel or iron or any other materials, ferromagnetic material. So, this ferromagnetic material, if it is in powder form, or it can be in rod form, or it can be in thin film, whatever. So, here there is a rod, here there is a rod. With this rod below, if it is powder form, this in straw. Okay. So, you put this material, or if it is film, or if it is bulk material. So, there will be sample holder, we attach this sample with this sample holder. So, this you can take a sample holder with sample. So, whatever the form of the sample, it can be powder, it can be thin film, it can be bulk material. Okay. So, this is the sample, it is so this sample holder is attached with a rod, and this rod is connected, here you can see, and this rod is connected here with a head of a loudspeaker. Okay. You know loudspeaker. So, to speak loudly, okay, we will speak normally, but people can hear loudly. So, through which this magnification is done, amplification is done, that is the loudspeaker. Okay. So, loudspeaker, I will tell the principle of loudspeaker. So, here this red one, so it is attached with this loudspeaker head. Okay. So, this is in a box. Okay. So, this is a box, loudspeaker box. Okay. So, this is the loudspeaker head. So, as a whole, this is the arrangement for loudspeaker. Okay. See, this rod is attached with this loudspeaker. Now, here now I have hanged my sample. So, this is the sample holder. Okay, and it is attached with this rod. Now, this rod is with the some loudspeaker head. Okay. Now, what I want to study? I want to measure the magnetization of this sample as a function of magnetic field. So, I have to apply magnetic field. So, I have to put this sample in magnetic field. So, that is what done. So, this is the pole pieces of a electromagnet. Okay. So, I have put my sample between the pole piece. Okay. So, from electromagnet I will apply magnetic field, and I will be able to vary magnetic field, and at different magnetic field what is the magnetization induced in the sample that I want to measure. Now, so now this I have to measure magnetization. I know the magnetic field, okay, from the electromagnet. I know the magnetic field. For this magnetic field, what is the magnetization? So, for a particular magnetic field, the sample is magnetized, means there will be magnetization along the magnetic field, and that magnetization I want to quantify. Okay. Now, this for measurement of this magnetization, we will use there are two ways to measure the magnetization. One is force method, another is induction method. Okay. So, here we will use induction method. In other experiment we will use force method. So, that I will discuss later on. Now, induction method means that this magnetization, okay, this magnetization, it basically magnetization is equivalent to magnetic field, because B equal to H plus M. So, H and M basically both are same. So, if you have magnetization, so it will generate magnetic field, means it will generate lines of force, magnetic lines of force, right. So, magnetic lines of magnetic force or magnetic flux, it will depend, it will depend on the strength of the magnetization. Okay. Higher the magnetization, higher the flux. Okay. So, now if I put a coil here, induction coil here, that is what I have put induction coil. Two coils, they are connected in both sides. We have put two coils. There is no physical connection. Okay. Now, Lenz this Faraday's induction law. Okay. What is that? If magnetic field or flux varies, then there will be induced EMF in the coil. Okay. If a coil in a magnetic field, now if this magnetic field varies with time, then there will be induction, there will be induced EMF in the coil. So, change of the flux with time will give induced EMF in the coil. Okay. So, due to this induced EMF, there will be current corresponding voltage. So, this induced EMF is related to the flux, flux is related to the magnetization, right. So, here whatever the magnetization, that magnetization will give lines of force, flux, and that flux will link with this coil, but then there will not be any induced EMF as long as you are not, this flux is not varying with time. Okay. So, I need to vary the flux link with this coil. So, that is why we have put this one on the loudspeaker head. Loudspeaker head, actually what it does, it is basically vibrate, loudspeaker. So, drum you have seen, when we drum, okay. So, sound makes because of the vibration of the drum. Okay. So, here this same thing, some drums, some spin kind of things is there. Okay. So, inside some arrangement is there. So, it is vibrating. Okay. so this drum, that screen also vibrating, so it's making louder sound. Okay. So in loudspeaker there are arrangement for vibration. Okay. So vibration with some frequency. Okay. So how it vibrates, that I will tell you, but so this is the arrangement to vibrate this sample. Okay, vibrate this sample. So I have coil, here sample. Now I have make arrangement for vibration of this coil. So what is happening? So this magnetization, due to magnetization lines of force, okay, now it is going out from this coil. So now there is no flux linked with the coil. So now flux with time, flux linked with the coil coming from this magnetization. So it's going from maximum value to 0, this flux changing with time. So d phi by dt. Okay. So how fast it is vibrating, so that is also important. So d phi by dt, and then from Faraday law, you know, induction law, induced EMF equal to minus d phi by dt. Induced EMF equal to minus d phi by dt. Okay. So so what happens? So I will get the induced EMF, I will guess the induced EMF, okay, in terms of say as a signal Vs equal to V0 sin omega t plus phi s. Okay. So why I have written sin? That if it is vibrating, whatever the way it is vibrating, if it is sinusoidal, it is vibrating with some frequency. So whatever the frequency here, that it will be same frequency as the frequency of this vibration of the loudspeaker. So if I give the frequency to the loudspeaker with this signal, okay, that V0 dash sin omega t plus phi r, some initial phase phi r. Okay. So if this sinusoidal signal is given to the loudspeakers for vibrating this loudspeaker head, sample is attached with this head, so sample also will vibrate with the same frequency. So this flux linked with this coil will vary with the same frequency, okay, and corresponding induced EMF I will get as a signal. So that's why here I have written this, say here AC signal, AC voltage we are giving, that is VR equal to V0 dash sin omega t plus phi r. Corresponding induced EMF I will get Vs equal to V0 sin omega t plus phi s. Okay. So you see, this experimental arrangement one has to make for fulfilling the physics law. Okay. So actually here I am converting the magnetization into the electrical signal. Okay. So the way magnetization or sample is vibrating, okay, I am getting electrical signal with the same frequency. So this is purely based on the Faraday's induction law. Now here, when we give AC signal to the loudspeaker head, then how it vibrate? Inside what is there? You know, loudspeaker. So here inside there is a coil like this. There is a coil, and inside and on top of this coil there is a permanent magnet, a bar magnet. Okay. So now AC signal in this coil is given, that is VR. So, sinusoidally it is varying from positive to negative, positive to negative. Okay. So, that means current in the coil is changing the direction, with time. So, this coil is equivalent to a magnet. Okay. It will have this north and south, and then with time it becoming south and north. Okay. So, with the signal, the polarity of this two end of this coil is changing. Now, we have permanent, it is all the time it is N and S. Okay. So, when this end is N, so there will be a repulsion, so it will go up. Okay. Then next cycle it is south. Okay. Then it will attract this one, north pole and south pole, it will come. Okay. For next cycle it is going up, coming down, going up, coming down. Okay. So, this way it is vibrating. Now, here that it is attached with this loudspeaker, that screen, as I told. So, that head, we tell loudspeaker, that head is connected with this permanent this bar magnet. So, this one is going up, as I have shown here, inside this box. So, this is vibrating, here in the box is vibrating. So, we are getting the louder sound. Okay. So, this exactly this we are using for our vibration of the sample. So, based on that, we are getting basically this AC signal, which is related with this magnetization. So, measuring this signal, induced EMF, that signal, we can find out the magnetization. So, one has to, so it's they are related, magnetization and the voltage. Okay. So, here you can see this, we tell the pickup coil, but yes. So, flux linked to the pickup coil, if it is phi equal to NBA. N is the number of turns in the coil, B is the magnetic induction, B is basically H plus M, mu 0 H plus M. So, applied field from this electromagnet as well as the field due to the magnetization. So, that is B equal to mu 0 H plus M. Okay. And A is the area. Okay. A is the area through which these lines of force are passing. Okay. So, this so it depends on the number of turns of the coil, it depends on the area of the coil. Okay. Area of the coil, and it depends on the flux, will depend on the, of course, the magnetic field H as well as this M, magnetization of the M. Okay. Now, this induced EMF, as I told, this is minus d phi by dt. So, Vs induced EMF equal to minus d phi by dt. Now, phi is this. So, N A mu 0 d by dt H plus M. Okay. H plus M, others, these are constant, number of turns in the coil, area of the coil, and mu 0, these are constant, and H also flux link with the coil. So, since these are permanent, this is the electromagnet, and all the time these flux are linked, and this electromagnet and these coils are fixed. Okay. So, flux due to this magnetic field H, that is not varying with time, that will not vary with time. So, it remain constant, it will be independent of time. Okay. And then this only flux coming from the magnetization, that will change with time, because this magnetization, that sample we are taking out and putting in, taking out, putting in. Okay. So, this only magnetization, flux coming from the magnetization, that will change with the time. So, that is why here you will get Vs equal to minus sign is there n a mu 0. If you say if now m it is a varying basically here how this. So, m that is seen or this m that is seen by the coil, okay, in which way it is seen with time. So, when it is here, then this it is seeing this m0. Now, sinusoidally it is vibrating, right. So, now sinusoidally when it is here it cannot see, okay. So, it is varying with they say sinusoidally. So, this coil will see this like m0 sin omega t, m0 sin omega t, okay. So, maximum that is m0 t equal to 0 time sin omega t 0 this or cos, I think it should be cos. So, at t equal to 0 then you are getting this cos omega t, cos t equal to 0 at time 0 it is a cos omega t 1. So, m0, okay. Now, it is going up, okay. At t to the power 4 this complete t to the power t by 2 at time t by 2 here, then again at t here, okay, t by 2 at that time omega t by 2 that will be 0, okay, omega t that will be again 1, okay. So, this way it is vibrating sinusoidally and this coil will see like it will see like m0 cos omega t. So, but or sin omega t depends starting from where you are starting. So, if your starting point from here, so then it will be sin omega t. If starting point from here, so it will be cos omega t. So, it does not matter. So, here I have written sin omega t, but one can write cos omega t. Then if you do differentiation d by dt, so it will be I think I should write this cos omega t, okay. I will write cos omega t, then it will be sin omega t, okay. It will be sin omega t and this one that omega 0 and this minus sign will be plus, okay. So, now this Vs equal to here you are getting this constant term, this we are writing V0, m0 here. So, all these are constant terms. So, we are writing this V0 sin omega t, some initial phase may be there phi s. So, that is why signal I have written here Vs equal to V0 sin omega t plus phi s, okay. So, in V0 basically you see this m0 is there, m0 is there. So, magnetization is there, okay. So, V0 equal to one can write n a mu 0 omega m0, okay. So, I want to measure m0, m0 is related with the V0, okay. So, if I can measure V0 or Vs, so I will get m. So, thus at different magnetic field magnetization will be different, Vs will be different, okay. So, I will get the magnetization as a function of magnetic field using this instrument. It is called VSM. Why it is called VSM? Now it is clear, because the principle of this magnetometer is that vibrating of the sample is the main part. If sample will not vibrate, you will not get any induction, you will not get any voltage, although you have magnetization. So, VSM, vibrating sample magnetometer. So, that's why this is the name. Okay. So, experiment we will do here, just this is the, you can take, this is the schematic of the experimental setup. So, this is the schematic diagram of the setup. So, basically electromagnet. Okay. First we have to calibrate the electromagnet, okay, using the Gauss meter, that is the first work, and then secondly we have to vibrate this sample using the loudspeaker, and corresponding induced AC signal we will get, and that AC signal we have to measure. When we will measure this AC signal, we will get this voltage, and voltage is proportional to the magnetization M, because V, as I told, V that is related with this part, no, V0, that is the M0 is there, M0 is there. So, it is basically other term are constant. So, V0 is V or Vs is proportional to the magnetization. Okay. So, generally we use known sample, nickel sample, okay, to calibrate this this voltage and the magnetization. Okay. For known sample, nickel sample, if I know the magnetization of that one for a particular saturation magnetization, say, of this sample, I will put that sample first, and I will note down the corresponding signal voltage. Okay. So, now that proportionality constant, magnetization is proportional to V. Okay. So, that proportionality constant I will find out this from known magnetization and corresponding measured voltage. Okay. So, then for unknown sample one can do the experiment. So, I will demonstrate this experiment using VSM in our laboratory. Okay. Thank you. I will in next class I will demonstrate.